Sri Naraj to speak on RF MEMS devices. We welcome you, sir.
Thank you, sir. Thank you for the introduction. Okay. So, first of all, I thank all the members of Institution of Engineers, Salem Division, for inviting me for the Engineers Talk series. Thank you very much. Okay. Share the screen. Sir, is it visible, sir?
Oh, yes, sir, visible.
Yeah, okay, thank you. So thank you, sir. Thank you for inviting me. Okay. So shall I start, sir?
Oh,
Yes,
yes,
sir, please, sir. Yes.
Thank you, ma'am. Okay. So I'll be giving an insight on what is RF MEMS device, right? So the content what I'm going to present here is on what is MEMS device, what is MEMS first of all, and then what is RF MEMS, and then I'll see some applications on MEMS devices and what are the materials we will be using for MEMS device, and finally we'll go on with RF MEMS devices. Right? So this is my overview of my presentation. So what is MEMS? So MEMS is nothing but micro electromechanical system, right? So basically this the size, or we call it as scaling. So it will be in the range of micrometer to millimeter range. And this electro is nothing but both electrical and electronic components with a mechanical action. So normally a MEMS is defined as a system that comprises of electrical, electronics, and mechanical on micron scale fabricated on a single silicon substrate. So this is how we define micro electromechanical systems. So these are some of the devices that has been fabricated on using MEMS technology. So the products that has been developed mostly include pressure sensors, temperature sensors, accelerometers, gyroscopes, and many sensor devices. So first, when the MEMS was developed, most of the devices that has been manufactured or developed was sensors, and this started since 1970s onwards. And the very important thing in MEMS is nothing but it should have a mechanical functionality like actuation. So actuation means there should be some part in this MEMS device which should have a movement. So this is what we call it as mechanical functionality. And defaultly, this is going to be a miniaturized system. So that is why we simply call it as mechatronic, electronics and mechanical. So we call it as mechatronic system. And the fabrication technology, as we see, this is a technology. There is no specific technology available for fabricating or manufacturing a MEMS device. So the MEMS technology was developed first with implementing VLSI, the use of VLSI technology, and with the little modification on based upon the applications, we modify with some addition or subtraction of the technologies. So the basically MEMS technology is nothing but a modification of VLSI technology. And you can create any miniaturized embedded system. So let us see what is MEMS first. So MEMS. So first word in MEMS is nothing but micro. As I have told you, micro is nothing but it represents the scaling of the device. The scaling typically it is ranging from 1 micrometer to 1 millimeter. See, you can imagine the size of a any component that is ranging from 1 micrometer to 1 millimeter. So we can see that 1 millimeter scale in that 1/10 of the division is 1 millimeter. So Imagine the scale. Even if it is in the micrometer range, imagine the size. It is 1000 of a millimeter. So I have to manufacture a device in such a very small scaling. So this is not conventionally possible with any technologies, any fabricating technology, semiconductor material, semiconductor design or industry technology. Next is electro. The second word electro stands for electrical or electronic component functionality. So it can be an electrical function like motors or anything, or it can have an electronic functions like switching operations, whatever. But the main important thing is it cannot be purely electrical or it cannot be purely electronic components. So it should have some mechanical functionality. Mechanical functionality is nothing but you have to transfer some, say, a force or a voltage that has to be converted into a force so that there is a mechanical action. So this is the word mechanical stands for. So system. So I'm going to integrate everything. So an electrical component, electronic component. So with the mechanical functionality like movements, everything put together as a system in micron scale. This is a MEMS technology. Now, with the MEMS technology applied for radio frequency applications, we call this MEMS technology as RF MEMS technology. So RF stands for radio frequency, and the frequency ranges from 3 kilohertz to 300 gigahertz. So you can imagine the wavelength of a device that is going to operate at 300 gigahertz. So it will be in micron scales defaultly. So you know that frequency is inversely proportional to wavelength. So as frequency increases, wavelength is going to decrease. So I need to have a component that has to be used for high frequency applications. Right? So this is the main aim of this RF MEMS. So the devices that has been manufactured using this MEMS technology for applying in radio frequency is what we call it as RF MEMS. Right. So what is the function of a MEMS? So you can see that in this diagram, you can see that MEMS functionality will consist of controlling motion. Then you have a radiating motion of micro devices, then sensing security. So defaultly, we call this as a sensors. Right? Simply, you can say all these functionalities is available in a sensor. So the main functionality of a MEMS device or MEMS technology is to convert a physical into an electrical or mechanical operations. Right? So the mechanical operations what mechanical operations means, it can do actuations, sensing, or any other functions. So what is this electronic components? What is going to see? We see that there is a miniaturization in size. So initially, when started with the mobile phones, now every day we are every day-to-day life we are using mobile phones. So in 20 years back, look at the size of a mobile phone what we were using, and look at the mobile phone what is currently available in the market. You can see that the minimum size, that is the thickness of the mobile phone, has been reduced less than 1 centimeter. And in the current market, the least thing that is available is 5 to 6 mm. So this is the least thickness of the mobile phone. In order to make the size or thickness that has to be reduced, what are the modifications that has to be designed in this mobile phone? So these are the RF MEMS devices. One of the best application where we can see is incorporating this wireless transceivers miniaturization. Right. So one of the main thing, this is the application where RF MEMS device is widely used nowadays, and there are many other applications also. But why I'm concentrating on this mobile phone is we are using it day to day life. So to have these devices, what are the motivations that has to be there? So one main important thing is the integration with electronics on a single chip. So I need to have everything on a single chip. This is the thing. So a mechanical action, a wafer or whatever it may be, a switch, an amplifier, everything fabricated on a single chip using a single material. This is the greatest challenge we face while miniaturization. So everything on a single chip, with a single material. This is the biggest challenge that has been faced while these MEMS devices are fabricated. The next one is I want to reduce the size of the cost. Sorry, reduce the cost. So production cost has to be reduced. So even I can manufacture a device that is of very low cost compared to the current market rate. So that is only possible with the help of bulk processing. What is bulk processing? Bulk processing is nothing but the scaling. It's not scaling. The number of components that has been manufactured. So one simple example I can say is I'm going to design an antenna. The cost of antenna that is fabricated for a single antenna is equal to the cost of manufacturing, say for example, 1,000 antennas, or say for example, 100 antennas. So if I'm going to produce a device that is used fabricated using MEMS technology, the cost of the component is going to be very high if I produce it in low quantity. So bulk fabrication is the only thing where these technologies can be widely implemented and used. And the third important motivation for a MEMS device is many unthought futures and products can be possible. Earlier in a VLSI technology or any other technology, the design constraint will be there. So we cannot manufacture a device that is of say zigzag shaped or any other shaped manner, round, hexagonal. It will be very difficult for us to manufacture. But this MEMS technology has proven a very challenging place in fabricating any sort of structures that is possible. And the last one is a combination of MEMS with other branches. Not only this MEMS device has been used in mechanical applications, it has been moved towards from sensors to RF side, optical MEMS, bio MEMS. Nowadays, this bio MEMS is playing a wide role in saving many of our lives. Right. So we will see some of the applications on this. So some of the applications where these MEMS devices used are in automobiles, where we can say nowadays our airbag system, airbag deployment system is there. Can see all our high-end model cars are having tire pressure sensors. So many sensors that has been used in cars or automobile dashboards, car dashboards are using MEMS sensors, right? And this tire pressure sensor is currently available in market, where you can see that this sensors can be procured within say 1,000 rupees. Next application is computer printers, cell phones, lab on a chip, where you can see nowadays you can see that that is your corona test chip kits are available. Optical devices like micro mirrors, where these are mostly used in mobile phones and projectors. So these are plenty of applications. There is usage of MEMS devices. Say some of the applications I will say for a MEMS device is MEMS accelerometer, right? So in this diagram, the left side diagram, you can see that the chip MEMS accelerometer chip is placed on a 1 cent coin. See, look at the size of the coin and look at the chip size. So this is somewhat similar to a new 1 rupee coin in India. See a very small size accelerometer. Then you can see an inkjet printer heads where the inks has to be sprayed. So the holes in the inkjet head, the printer head should be very minute. So this is one of the biggest challenge in computer applications. So the MEMS technology has proven a way for spraying the inks from the inkjet heads. Okay. And the one of the third applications what that has been displayed here is a micro mirror, where these micro mirrors are widely used in optical, say for example, projectors. See, even nowadays, all our theaters has become digital. So we have a laser projector that is projecting the movies, and you can see that the clarity of the image that is shown on the video that is shown on the screen is fantastic. So thanks to the micro mirrors, and we can see the LED TVs nowadays. When the LED TV was introduced, there are a lot of gaps in between. So you can see that LEDs are packed compactly. Even though it is packed compactly, there are large things. When you look at the look at the TV in a side angle, you can see that there are large gaps. So these gaps are nowadays filled because of this micro LEDs that has been placed. The size of the LED has become very small. So the TV screen in the inside the TV screen, the LEDs are very compactly placed. So the gap between two LEDs are very minimum. So with this, you can improve the clarity of the image. And another important application we see is pressure sensor. So this is a sensor that is used for say tire pressure monitoring. So the air pressure is applied, and this pressure varying the piezo resistance or resistance of the uh, material that is fabricated above the sensor. The variation in resistance will give the tire pressure sensor. And another one is a cantilever beam. This cantilever beam we'll discuss in RF MEMS switch in detail. Okay. So this is one of the widely used MEMS device that is used in uh, airbag deployment system in a car. So when a car hits a object heavily, you can see that. So what is the use of the airbag? What is the principle of the airbag deployment system? So when there is an acceleration, or when this sensor hits something, then the airbag gets deployed. So this airbag the sensor airbag deployment sensor, you can see here that is shown in the blue color. This is a chip that is less than the size of an rice grain. So you can see a rice. Take a rice, look at the size. This chip is going to be less than the size of the rice grain. Okay. So to make a better understanding of MEMS device, this is a best example for defining what is a MEMS technology. So this is a micro car. So look at the image that is shown in this slide. So there are some rice grains that has been placed, and this micro cars is placed near the rice grain. Look at the size of the rice grain and look at the size of the car that has been fabricated using MEMS technology. And this is not a playing car. This car will run, right? So I'll show the next image. Okay, see the car that has been placed in an 1 cent coin as well as on a matchstick. This images are taken using scanned electron microscopy, right? See, look at the specification of this car that has been fabricated using MEMS technology. The weight of this car is going to reduce. Weight is also going to get reduced. Next, look at the dimension. It is 4.7 mm cross 1.7 mm. So it is less than 5 mm size, right? So it works basically. It has an electrical motor inside this car, and this electrical motor is controlled via a remote control, so that the car can run. So this car is not used for any commercial application. This is only to show that the MEMS technology can be used for any applications. And you can see this is a Japan-based company called Denso that has fabricated this car. You can Google in you can Google it, the car that will be moving. So coming to the MEMS fabrication technique, there are two important fabrication techniques that been used in MEMS technology. One is bulk micro machining and sorry, another one is surface micro machining. So what is bulk micro machining? So bulk micro machining is nothing but I have a material, I just etch away the material and create a device. So that is etching means removing the surface of the material, and I am going to carve the device that what I want to manufacture or fabricate. Next one is surface macromachining. Surface macromachining is something like what we deposit some other material or something on the above the surface of the material, and a product is developed. So bulk micromachining, we are removing some of the regions of the material. Surface micromachining, we are depositing. So any structure can be possible. That is why MEMS technology has proven one of the salient technologies nowadays in creating any device. Right. So earlier we had VLSI technology where that is limited to certain constraints or some design limitations. Where this MEMS technology has proved using VLSI technology, any structure can be fabricated. So this is a micro machining process where one of the main important thing in this MEMS fabrication is we need a clean 100 or clean 1000 room. So we cannot have a room that is dirty or anything. So it should be so clean. So clean 100 is nothing but one part in 100 particles will be a dust. So out of 100 particles, only one particle of dust is possible. So that much amount of clean environment has to be there. So this is a fabrication process flow. I want this like a planar material. This device has been fabricated. So first I take a planar substrate material. I put a mask on what type of structures. I put an X-ray radiation to harden that. Then that is etched away using either wet etching or dry etching. So wet etching, I put some chemical solutions so that it will get etched away. And finally, the side regions are removed. And finally, I get with this MMA material. So this is a material that is used in for mechanical operations. So the fifth one is the final end product. So from the first product, the step-by-step process of fabricating this MEMS device is shown here. So by looking at you don't assume that the size of this is going to be too large. This size is going to be in less than millimeter scale. So the materials what we use in this MEMS technology is the metals, normally aluminum, gold, copper, silver. These are the most commonly used metals in MEMS technology. And insulator, for an insulating medium, we use either silicon dioxide material or silicon nitrates, most commonly used insulating materials. And to reduce the size, the polymer materials are used. So in order to have some applications having reduced size as well as weight, polymer materials are used. And the most commonly used and very important material that has been used in MEMS is silicon. The silicon can be anything. It can be a single crystal or a polycrystalline silicon, doped silicon. And the very important feature of the silicon is it is very much stronger than steel compared to that thickness of, say, for example, 200 micrometer or 500 micrometer. And the thickness ranges between 10 nanometer to 10 millimeter. And the another important product or a material that is used for making this product or MEMS product is tin. Tin is a very, very important material that is used as an adhesive. So to paste two materials, this tin material is used. So now coming to RF MEMS. So RF MEMS, so I need all this MEMS technology to be implemented for use in radio frequency components. So the components that are the devices that has been used, that has to be used at radio frequencies, then the size will automatically get reduced, because we have seen that the radio frequency is ranging from up to 300 gigahertz. So when the frequency increases, defaultly wavelength is going to reduce. So wavelength is nothing but the size of the component at RF frequency. So the most commonly used devices we use are MEMS switches, inductors, capacitors, antennas, filters, resonators, etc. So one of the biggest application where we see here is in the RF MEMS is we can see a wide applications and wide markets available for RF MEMS products like electronics where GPS. Every mobile phone has GPS. Every cars nowadays, all the cars is having GPS. Then you have RFID tags, millimeter wave sensors. Then all the sensors that has been used in cars. Then you have a transmission reception mobile phone. One of the best application is mobile phones. Then you can see that all the wireless LANs that has been available in the mobile Wi-Fi modules and your in your laptops, the size has to be reduced. So once the size has is very much reduced, the one of the very important application for reduction in size is going to be the longer, life of the battery. So once the size is reduced, power consumption is reduced. Once power consumption of the component is reduced, automatically battery lifetime is going to be longer. So that is why nowadays you can see that a mobile phone with 5,000 milliampere battery is going to work for longer duration. Even when I use a battery of 5,000 milliampere hour, then this battery will drain quickly. So there is no much important much thing while replacing a 800 milliampere battery 20 years back to a 5,000 milliampere battery. Along with the battery replacement, you have to change the components that has to have a low power consumption. This is one of the wide challenge in RF MEMS technology. Another applications we have seen is antennas and satellite communications. So these are some of the wireless appliances with some information sources. We can say for voice, you can use cell phones, videos, you can have digital cameras, broadband data, you can have laptops, messaging, we had earlier pages, navigation, we have GPS receivers, DBS, we have televisions, direct broadcast systems, we have televisions, internet, we have. Now you can see that all these informations, all these items that has been displayed is now available in our mobile phone. A single device that can be used for all these information sources. So all these informations we are seeing in a single device, then the device. So all these mobile phones work on the battery. So the lifetime of the battery depends on what we use. So so in order to have a longer duration of battery and long life, we have to have a device that has to consume low power. So all the components that is available in the mobile phones are mostly now replaced by the same components using MEMS technology. So this is a block diagram that shows how all our mobile phone components are now replaced. These colored components, the block diagram, in the block diagram, the colored components are now replaced by MEMS components. So this is a block diagram of a transceiver where transceiver is nothing but you have a transmitter as well as receiver. So this is the setup that is available inside our mobile phone. Your PCB has this setup, right? So we had two antennas, antenna one for transmitting and another one for receiving. So you have a switch that has to switch between antenna 1 and 2 to make your antenna either working as a transmitting antenna while we speak, and while we hear from the opponent, then this switch has to move to antenna 2, which is acting as a receiving antenna. So this switch earlier we had is an electromechanical switch, which is larger in size, now has been replaced by a MEMS switch, which is of very micrometer size scale. And you can see that this band pass filters, then you can have a transmitter receive switch, then you have a band pass filter, sorry, low pass filter, you have a high pass filter, intermediate filters, inductors, capacitors, resonators, all these components, whatever that is available in the electronic industry, can now be replaced by the same components using MEMS technology. So one of the greatest advantages is size is reduced. Defaultly, our mobile phone or any electronic product which is implemented using MEMS technology, the size is going to reduce. At the same time, weight is going to reduce. At the same time, power consumption is going to get reduced. So these are the advantages why these are replaced by, mm, why these components are replaced using MEMS technology, such that the lifetime of the component can improve. So what are the MEMS components? You can see that inductors, variable capacitors is nothing but varactors, transmission lines, switches, resonators, oscillators, mixers, power amplifiers, phase shifters, filters, antennas, smart antennas, transceivers, everything. So all these components is available in our mobile phone. So these components are now replaced by MEMS technology. So this is one of the applications of MEMS, the RF MEMS device, a MEMS switch. So I'll show you a MEMS switch. So this is a MEMS switch. So you can see there is a center line where you can see a signal line, right? So this signal line is input, and this is a output of where the signal comes. So this is a signal line, and these two lines are ground. So I want to make this act as a switch, means what? So when there is no contact between these two grounds, when the signal is passed through the signal line, the signal comes out from the other end. So we call that the switch is in on state. Okay. Look at the second diagram. When I put a pressure on this, right? So when I put a pressure on this part, you can see that the ground plane is pressed towards the center conductor or a signal line. So defaultly, the ground comes in contact with the signal line, and the signal cannot pass through. The switch is in off state. So this is one of the applications of MEMS switch. So you can see that so I can see that the switch is going to move. So this is a diagram. So you can see that this is the upper membrane. So when this membrane is pushed down, it comes in contact with the conductor. So the signal is grounded. So this is the basic principle of a MEMS switch, where I make on and switch on and off with the help of a membrane that is going to move up and down. When the membrane is up state, the switch will be in on state. When the membrane is in down state, the switch will be in off state since the signal is grounded. So this is the going to be the membrane. Says this MEMS membranes that has to be pushed down and up cannot be done with the help of any external source. We have to apply a control voltage. This control voltage will create an electrostatic force between the membrane and the center conductor, and it tries to push or pull. So with the help of this control voltage, we can make this up and down. So the biggest challenge what we faced in designing a MEMS switch is how much amount of control voltage. When I implement the switch in a mobile phone for an antenna switching between transmitter and receiver, the mobile phone battery is only 3.9 volts or maximum 5 volts. So we have to have a switch that has to be controlled within this 5 volt device. So this is the biggest challenge that has been faced while designing a RF MEMS switch. And nowadays we can see that these switches can operate less than 1 volt. So this is the achievement in RF MEMS technology. So the another one is one of the application is RF MEMS phase shifter. So instead of one membrane, I just place more membranes. You can see that can see 6 membranes that has been placed on the thing, and each membrane is actuated to move up and down. So the velocity of the signal that is traveling in the port 1 to port 2 is going to get varied. So once the velocity is going to get varied, automatically there will be a change in phase. So there will be a change in impedance of the transmission line. So this impedance will cause a change in velocity, and this velocity will change the phase shift. So there will be a phase shift that is occurring. So input signal will be of some phase. The received output signal has a varied phase. This is one of the application where this has been used. This MEMS technology has been used in phase shifters and phased array radar. So this is another important application of in digital phase shifter. Where digital phase shifter, we can see a 45-degree phase shifter is there, and 90-degree phase shifter is there, and 180-degree phase shifter. So I can tap out at different outputs. So one output will be a 45-degree, one output will be a 90-degree phase change, and another output will be a 180-degree phase change. So wherever and say what modulator is there, we need a sine signal and a cosine signal. I cannot use two different signal generators for generating a sine and cosine because signal generator is too costly, too expensive to implement. So if an electronic device having more number of signal generators, then it is it will become costlier. Right. Okay. And next one is a very important application that is tunable inductor. So tunable inductor, we can see that the inductor will be in coil shape. So if it is in a round coil, the size of the component that is placed on above the PCB, the thickness of the PCB or the component will get increased. So I have to find out an alternate method so that this inductor has to be placed in a planar surface. So planar surface means it should not be like a round coil. It should be something like a square, so that is placed above the PCB will get me a reduction in thickness of that electronic component after packaging. So this is the right side diagram shows the planar inductor. This is also a tunable inductor where I put an MEMS switch over this so that I can vary the inductance value also. So this is another important device that is used in RF application. Next one is an RF MEMS varactor where this is nothing but a variable capacitor. So I want to vary the capacitance. So capacitance is nothing but two electrolytic plates separated by some distance. So you can see so this is one electroplate and this is another electroplate separated by some air gap. So I can vary the height of this height can be varied so that the capacitance can be varied. So capacitance is nothing but you can see it is given as epsilon naught A by G. Right. So this gap is varied. So this is the gap. So this gap is varied. So automatically there will be a change in capacitance. So this change in capacitance will definitely act as a varactor. And if I fabricate in this model, then the size of the component will be in micrometer scale. And this is practically been implemented and this has been fabricated and this has shown a very good output. And another one is phased array antenna. This phased array antenna is a current trend. So in current research, there is a lot of work that is going in phased array antenna, where we use these antennas for radar applications. And in this radar application, these antennas or this device is going have to be taken to a bar field. So army man carrying this antenna, uh, uh, so the size of the on his shoulder, so the size of the antenna has to be reduced, as well as the thickness has to be reduced, so that weight has to be reduced. So with the MEMS technologies, I can design an antenna, I can have a phase shifter with millimeter or micrometer size. So this phased array antenna will have thousands of antennas placed on a array like structure, like a matrix form. So a 100 cross 100 antenna phased array will give me a 10,000 antenna, with each antenna rotating a signal to phase of, say, the total phase shift is going to be 360-degree. This is going to have 360-degree divided by 10,000 antennas. So each antenna will give a very minute phase shift, so that any aircraft that is traveling above can be tracked by this radar. So this is one of the current research that is going on. One in signal processing, and another one is RF MEMS antenna, or RF MEMS phase antenna with phase shift. So there are two large researches that are currently going on in phased array antenna. One in signal processing applications. So the RF source is the another signal processing application, and the second one is this phase shifter and antenna design, so that the size has to be reduced. Right. So these are some of the applications that has been used by in communication systems or wireless transceivers using MEMS technology. Now, the advantage of using RF MEMS technology is higher performance. The performance is going to be fantastically good compared to the conventional electronic fabrication technologies, because the size reduction, power consumption, loss is very low, then low power dissipation. This is a very important advantage. So you have any component with increased selectivity, high quality factor for inductors and capacitors, loss is reduced, better isolation, low distortions. So isolation plays a very larger role in switches, and in communications like amplifiers, increased bandwidth is obtained, antennas increased bandwidth has been obtained. And since the size is small, you have low power consumption. We go for batch fabrications, so the cost can be reduced drastically. And finally, a single IC that contains all these components fabricated and packed in a single IC. So this is one of the greatest advantage of MEMS technology in electronic industry. And so if there is this technology, a new technology means there will be some advantages as well as there will be some limitations. So we have seen the advantages, which has a fantastic advantages compared to the conventional electronic component manufacturing. Now you'll see some of the limitations that that has been faced by the MEMS technology. So this MEMS device cannot handle very high power. So all this, since the size is very small in micrometer or millimeter range, the size is going to be very small. So the power handling capability is also limited. So I cannot go and use it for applications like kilowatt range. And the initial establishment cost is going to be huge. So I need to set up a fabrication center. I need to have crores of rupees. So that is going to be there. But currently, a lot of industries and government agencies are available for manufacture. So we give the design, they will manufacture and give us. And the polysilicon material, we can say it is a brittle material. So it is having a large impurities. And the design process involves complex procedures and processes. Defaultly, every one of us know that any semiconductor industry, the fabrication process is going to be tedious. So from the cleaning of the material to finally a packaged device, everything is going to be tedious. Any one mistake in between will we have to scrap that product and we have to start with a new process, starting from the initial stage. And finally, packaging. So packaging plays a wide role in MEMS technology. Right. So we cannot have a device pack material that is used, plastic material that is used for fabricating a chip, so that it can easily break. So that cannot be so that material cannot be used in packaging. So packaging plays your size of the component is in micrometer, but when I look at the final product after package, the size will be like a small chip size. So it will be of 3 to say 1 centimeter or 0.8 centimeter size will be there. But inside that, the MEMS device that we manufactured is going to be only a few micrometer to millimeter range. But after package, that size will be little bit larger. So this is one of the limited. These are some of the limitations of MEMS technology. Right. So that's all from my side. Okay. So I have given. I hope that I have given some insight on what is MEMS technology and what are the applications. Mainly, I have spoken about rather than fabrication technologies. I have spoken on what are the some of the MEMS applications, and then I have talked about what are the RF MEMS devices that is used in current electronic industry. Right. So that's all from my side. If you have any queries. So any queries?
Yeah, participants, if you have any queries, please you can directly ask with our expert.
So since time is limited, I cannot briefly elaborate the fabrication technologies and other things. So I have just given an insight on what is MEMS device and its applications.
Okay, well, sir, we are very much thankful to you because you have really taken the session with more illustrations, and that is reason for no doubtedness. Okay, so thank you very much, sir.
Thank you, sir.
And now I request the Honorary Secretary, IEI Salem Local Center, to propose vote of thanks.
Thank you, sir. Sir, I'm audible, sir?
Yes, ma'am. Yes.